Good morning. Today we'll discuss about Faraday's laws of electromagnetic induction. In the last lecture, we have discussed about the magnetic materials, the different types of magnetic materials, ferro, ferri, antiferro, paramagnetic materials, and we have also seen magnetic boundary conditions also. In this lecture, we will discuss about the Faraday's laws of electromagnetic attraction, which are very important for electrical engineers. I hope that by the end of this video lecture, you will be able to determine the EMF which is induced in a conductor subjected to given magnetic field. So, coming to the introduction, Faraday's law states that a current will be induced in a conductor which is exposed to changing magnetic fields. So before going for this one, let me give you a small introduction. Why I'm going with this Faraday's laws of electromagnetic induction. In unit number 1 and unit number 2, we have seen that electric fields develop voltage. Magnetic fields also we have seen. These are due to currents, right? A current develops a magnetic field, whereas a voltage develops an electric field, right? In unit number 4, we will cross these two things, electric fields and magnetic fields, and we will see that a magnetic field can develop an EMF, or which we call it as a voltage. And this voltage, if it is provided a closed path, we can develop a current, which means we are able to develop voltage and current, which we call them as power or electrical energy. So now we are going to generate electrical energy with the help of magnetic fields. This is what our major intention is in going with the unit number 4, in particularly the Faraday's laws of electromagnetic induction. These will give you knowledge about how electrical energy is being generated. So moving ahead, first of all, let's stick on to the statement of Faraday's laws. Then we will see how we can apply them for our electrical engineering. First of all, the Faraday's law, they state that the current will be induced in the conductor which is exposed to a changing magnetic field. See, this word is more important. Changing magnetic fields. And there is one more law which supports this concept of generation of electrical energy. We call it as a Lenz's law, which states that the direction of this induced current will be such that the magnetic field created by the induced current, it opposes the initial cause of it. And the direction of this current flow will be determined by Fleming's right hand rule, that also we will see in the class. So first of all, where we will employ this Faraday's laws. These are employed in transformers, motors, generators, etc., inductors also. All these devices, the electrical devices which we come across daily, they will employ this Faraday's laws of electromagnetic induction. And this law is named after the famous scientist Michael Faraday. He observed these mechanisms when he was doing experiment with a magnet and a coil. He discovered that when a coil is moved in a magnetic field, EMF is induced in the coil. So he formulated two laws which are famously called as Faraday's laws of electromagnetic induction. Now, the first law, what he told us, any change in the magnetic field of a coil of a wire will cause an EMF to be induced in the coil, which means that there is a coil and there is a magnetic field. So any change in the magnetic field which is experienced by this coil, automatically this coil used to have an EMF. In particular, they called it as an induced EMF. And if the circuit was closed, then a current was flowing in this circuit, which we called it as induced current. So he observed that just there was a magnetic field and there was a coil, and coil was experiencing a variable magnetic field, then automatically current was flowing in the circuits. And he stated one more thing, that the amount of current or the amount of EMF is proportional to or is equal to rate of change of flux linkages, or I'll call it as, I'll take it as d psi, which I'll take it as, if there are n number of turns, I'll take it as d phi by dt. This is flux per turn into number of turns. So this is the magnitude of the EMF. This are the two Faraday's laws which he proposed, which were proposed by the Faraday. And yeah, this is the expression. Let us suppose if this indicates a flux linkages, the induced EMF is equal to minus d psi by dt. And if flux linkage is equal to number of turns into flux per each turn. This is flux per each turn. This is the equation here. Okay, so now your equation now becomes, normally the number of turns is a constant term, so I'll remove this one. So I'll get minus n d phi by dt, where flux phi indicates flux per turn. Okay. Now, if there is only one turn, then n becomes 1, so you'll get this equation. Do remember, EMF is induced when the flux changes. Now, the relation between V and D, you know that the relation between V and D, E indicates a flux, electric field intensity, right? You know that we do already have the V and D relation. We have seen in unit number 1. The relation between V and D is V is equal to minus E dot dl. Right? So now this voltage is nothing but our induced EMF in this case, and it is equal to minus n d phi by dt. Right? Now let us try to equate these two equations. This is related to the electric field and this is related to the magnetic fields. Now, if I relate these two equations, what I'll get is V was equal to minus E dot dl. Right. At the same time, it was equal to minus n d phi by dt. Right. So this one we can apply Stokes theorem. This closed integral, it can be converted into open integral with, right. This was the expression. Right. On the right hand side, this n d phi by dt, we can write it as dy dt. Right, we know that phi is nothing but, phi is nothing but, it is surface integral of, right, this is the surface integral of b dot ds, right? So, where b is nothing but flux density, magnetic flux density. So, I am going to write this one. So, what I'll get here, this is minus n integral dv by dt dot ds, isn't it? So now the same voltage in case of electric field, this is the expression. In case of magnetic field, this is the expression. Now I will equate these two now. If I equate these two, so integral del cross E dot ds is equal to minus surface integral of dv by dt dot ds. So if I remove the surface integral, then this is my final expression. This is called as Maxwell's equation for time varying fields, the interrelation between the electric field and the magnetic field. So I can write this one as del cross E, this is minus mu dh by dt. This is the relation between magnetic field intensity and electric field intensity. Del cross E is equal to minus mu dh by dt. Okay, which means an electric magnetic fields which is varying with respect to time can develop an electric fields. This is the interrelation between electric field and magnetic fields. Okay. Now, this is case number 1, right? So I can take this one as this is V, right? This was the relation between del cross E and minus mu dH by dt, and this is the equation, right? Now, electric field can be developed when there is a magnetic field which is varying with respect to time. Now, let us suppose if magnetic field is constant, because if we do have DC currents and the magnetic field remains constant, in that case, do we have an EMF generated? No. Normally, when the magnetic field is constant with respect to time, and if the coil is stationary, we don't get any EMF. Now the second case comes now. So once again repeating for you guys, there is a conductor and it is placed on a magnetic field. For EMF to be induced, there are three cases. Case 1, conductor is stationary. Field is varying. Field is varying with respect to time. Field is varying with respect to time. Case number 2. This is what we have seen now. Stationary loop, time varying magnetic field. In other ways, conductor does not vary with respect to time, right? Conductor is moving in space, whereas field is constant with respect to time. This is case number 2. Case number 3, combination of 1 plus 2. When conductor is moving and also field is varying with respect to time. In the first case, conductor is stationary, field is varying with respect to time, which means that AC field. This is AC field, this is DC field. If it is an AC field, you just can keep the conductor stationary. If it is a DC field, then you should make some physical motion for the conductor or for the fields. There must be a relative motion between these two. So the first case we have seen, what is the field which is being developed? Del cross E is equal to minus dV by dt. Now we will move on to case number 2. When the field is constant with respect to time, but the conductor is moving with respect to space. So now, when a conducting loop is moving in a static B fields, which is constant with respect to time, an MF is induced in the loop because the conductor is moving. So we'll start with the basic equation. You know that when a charge, if it is moving in a magnetic field with a velocity of u, then this is the equation. Fm is equal to q into u cross p, right? Now this electric fields, if this is the force in the magnetic field experienced by the charge, if it is equal to the electric force, then you know that electric force is equal to q into E, right? Now this is the field, electric field, which is developed due to the magnetic field. I'll take EM. Electric field due to the motion now. So what I'll get, Fm was already q into u cross b by q. So what I'll get, EM is equal to u cross b. EM is equal to u cross b, right? So if I want to V, what is the EMF induced? Integral of L EM dot dl, right? So which is nothing but 1 u cross p dot dl. This is EMF, right? So I can write this one, del cross b is equal to del cross u cross b, right? Because I can apply, because VAMF, I know that it is equal to minus EM dot dl. This is equal to, so I can apply Stokes theorem again. This will, I'll get del cross EM, del cross u cross b. So either you can apply this del cross E, sir, right? So this is the equation for determining the EMF. Now when both the things are happening, which means that loop is moving and the field is also varying with respect to time, then I should join these two equations. The first equation was minus integral, surface integral of dV by dt. The second case, line integral of u cross b dot dl. So I need to join these two equations, right? So Depending upon your requirement, you can use any of these equations to determine the EMF which is induced in the conductor. So to repeat again, you can determine EMF when the conductor is stationary and the field is varying with respect to time, or the conductor is moving with respect to space and the field is stationary, or conductor is moving and the field is also varying with respect to time. So I hope that now you are able to employ these equations to determine the EMF and will solve the problems in the class. Thank you.